This formula is the Pearson product moment correlation. This is used in order to measure the degree of linear relationship between variables. For example, if you have variables x and y, and we would like to know how strong is their linear relationship, we can only use this formula if we can verify that there is indeed a linear relationship. And the way to do that is first to construct this scatter plot. We plot each of this pair of points. For example, when x is 1, y is 1, that is this point. When x is 2, y is 3, that is this point. When x is 4, y is 5, and that is this point. And when x is 5, y is 7, this is this point. This blue line is the line of best fit, and it appears that there is indeed a linear relationship between x and y. Now, if you as a researcher has reason to believe that the data that you have are inherently nonlinear, then don't use this Pearson R correlation because your interpretation would be wrong. Now, having verified that there is a linear relationship between x and y in our example, then we can now compute for the Pearson R. We start by constructing this table that can facilitate our application of this formula. We added 3 columns, one for the product of the two variables x and y. The next is for the square of the first variable, and the last is for the square of the second variable. Now, for each of these columns, we are going to compute for the column total. Here, we have the sigma x for the sum of 1 plus 2 plus 4 plus 5. We have the sigma y for the total of column y. The same explanation for the other columns. And the results of all these column totals are the one that we are going to substitute to this formula. So this sigma xy is whatever is the column total here. Sigma x is this. Sigma y is this value. For our n, we have 1, 2, 3, 4. Then for the denominator, we have this big squared symbol, and again is 4. Sigma x squared would be whatever is the column total for the column x squared. Now the confusion here is for this parenthesis sigma x squared. This means the square of the column total for x, which is this value here. Whereas for sigma x squared, that is the column total for the column x squared. Now the same explanation for sigma y squared and parenthesis sigma y squared. So to apply now this formula, we need to complete this table. We need to first multiply the entry for x and the entry for y row by row. So 1 times 1 is equal to 1, 2 times 3 is equal to 6, 4 times 5 is 20, and 5 times 7 is 35. Then we will square this column x. That means 1 squared equals 1, 2 squared is equal to 4, 4 squared is 16, and 5 squared is 25. Then for the last column, we are going to square this column here. 1 squared is 1, 3 squared is 9, 5 squared is 25, and 7 squared is 49. Then we compute for the column total. 1 plus 2 plus 4 plus 5 is 12. 1 plus 3 plus 5 plus 7 is 16. 1 plus 6 plus 20 is 27 plus 35 is 62. 1 plus 4 plus 16 is 21 plus 25 is 46. 1 plus 9 plus 25 is 35 plus 49 is 84. Then from here, all the rest is just substituting these values to the formula. So substituting now these values to the formula, we have r equals this n is equal to 4. Then this sigma xy is this value here, and that is 62. This sigma x is this value here, which is 12. Then sigma y is this value, which is 16. Then for the denominator, we have n, which is 4. Then sigma x squared is the sum of the column x squared, which is 46, minus sigma x. Our sigma x is 12, and we square it, so we have 12 squared. And make sure you copy the minus sign. That is one factor. The other factor is n, which is 4, times sigma y squared, which is this column total, which is 84, minus sigma y squared. Sigma y is 16, and squaring it to get 16 squared. And don't forget the minus sign. All the rest is just arithmetic simplification. So multiplying now 4 times 62, we have 248. 12 times 16 is 192, and we copy the minus sign. 4 times 46 is 184. 12 squared is 144, and we copy the minus sign. For the last factor here, 4 times 84 is 336, and 16 squared is 256. Again, we copy the minus sign. Then, computing further, 248 minus 192 is 56. 184 minus 144 is 40. 336 minus 256 is 80. And 40 times 80 is 3,200. The square root of 3,200 is 56.568542 rounded off to 6 decimal places. And dividing now this numerator divided by the denominator, our value of R is 0.9899. This is now our Pearson R correlation. So what does this R value mean? Let's remember that for correlation, the range of values are from -1 up to +1, where +1 means perfect positive correlation and -1 is for perfect negative correlation and 0 for no correlation. Now, since going back to our data, we know that the scatter plot shows an almost perfect correlation. We expect R to be close to 1, and we really got a value that's close to 1. So this means that this R value represents a very strong positive correlation. This is almost perfect correlation. Now, if we square R and convert that to percentage, the result is 97.99%. This value now is what we call as the coefficient of determination. This means that about 98% of the variation in X can be accounted for by its relationship with the other variable, Y. But correlation cannot identify which one is the dependent, which one is the independent variable. Because you can switch X and Y in this case, and you will still get the same R value. Now, having computed our value for R, there are 5 things that I would like to emphasize here. And these are some of the misuses of correlation. The first common error is to assume that correlation implies causation. There is no cause and effect here. What the correlation measures is the degree of association between the two variables. So we cannot claim that the variable X is the cause why we observe the result in variable Y. There is no cause and effect here. The second common error is to use correlation for non-linear relationships. If you know, as the researcher, that the dataset are inherently non-linear, then do not use the Pearson R correlation. That is a misuse of this statistical coefficient. Let's remember that in our data, we plot first the points, and based on this scatter plot, we realize that there is indeed linear relationship, and so we proceed to the computation of the Pearson R. Next common error in using correlation is on relying on correlation alone and not trying any other ways to measure the relationship between variables. There are other methods of measuring the degree of relationship. For example, we have chi-square, we have regression analysis, and some other methods. Now, the fourth common error is ignoring the outlier. For example, in our data, if this 70 happens to be like 7 million or 700 or 7,000 or any big number, that number is the outlier, and that outlier can significantly increase the value of Pearson R. And another common error here is confusing correlation with prediction. Correlation is the measure of relationship between two variables, but it does not necessarily mean that one variable can predict the other. This is a measure of association. So thank you very much. This is Lando Assistant, and we hope to see you again in our next video. Bye for now.